You ever notice if you're standing outside, if you're standing near a road, as a car approaches you, the noises from the car, the pitch gets higher and higher? If the car's driving away from you, the noises from the car get lower and lower, the pitches. That's due to what we call the Doppler effect. The Doppler effect applies to any type of wave. We have different equations, though, depending upon what types of waves. Light, for example, will undergo a Doppler effect as well, if there's any motion. What?
Redshift, blue shift.
Yes, they're called the redshift and the blue shift for light. For any motion directly towards you or directly away from you, you will perceive a different frequency than is actually being emitted. The reason for that, let's say we have a siren on the top of a police car. It emits a certain frequency, which means that that sound also has a certain wavelength. Now, granted, it does change in pitch. If the siren starts moving, let's say it starts moving to the right, what happens is that pushes the peaks closer together. So not only does it emit the sound, but then it moves. So when it continues emitting the sound, the peaks now are perceived to be closer together. So the wavelength decreases. But does having a cop car that's moving make the sound travel any faster? No. It's the same air, same temperature. If the medium hasn't changed, the speed of the wave has to stay constant. So if the wavelength is getting shorter because of the motion, then the frequency is getting bigger because of the motion. So we hear, in the terms of sound, we hear a higher frequency than what is actually being emitted. If the sound, whatever is emitting the sound, is moving away, that draws the peaks out. It makes the wavelength longer, which in turn means the frequency we hear, in the case of sound, would be a shorter frequency. Okay. Now, this noisemaker doesn't have to be the one that's moving. You could certainly have the police car on the side of the road with its sirens on, and you'd be driving by, and you would still hear the same effect. As you approach the cop car, you would hear a higher pitch than normal. As you drove away, you would hear a lower pitch than normal. So the source can be moving, or the observer, the one listening, could be moving. Or they could both be moving. It doesn't really matter. Please keep in mind, though, we only notice the Doppler effect if the motion is directly towards us or directly away from us. Okay? If there's no motion directly towards us or away from us, so if we were standing and we had a cop car driving in a perfect circle around us, not that they would, but we wouldn't hear a change in pitch. We would hear the normal siren sound, the same thing we would hear if the cop was stationary. Okay? So the Doppler effect only works when there's motion directly towards you or directly away from you. So with light, for example, if you have a star that's moving towards us, the light that we see coming from the star, the wavelengths will be shorter than what we normally expect. If it's moving away from us, we'll see wavelengths that are longer. This would be called a redshift. On the visible scale, red has a longer wavelength than blue, so they call it a redshift. So if a star is moving away from us, the light that we receive from it will be shifted to the red end. If it's moving towards us, we call it a blue shift, because the wavelengths are shifted towards the blue end. Now the equations. For sound, the equations for the Doppler effect are different for sound versus light. They're very, very similar, but they are not the same. For sound, your book gives you 4 different equations. One equation if your observer is moving and observer moving and the source is stationary. They give you an equation for towards and an equation for away. And then they swap it and say if the observer is stationary and the source is moving, they give you an equation towards and away. Turns out there's a way to combine all the equations and make it one nice, pretty equation. I'm going to give you that one. explain all the terms here, just 1 second. Let me make sure I got the observer and source in the right place. Yes. Okay, F naught is the actual frequency that you would hear if there was no motion involved at all. So if everyone was stationary, that would be the actual frequency emitted by whatever's making the noise. Maybe it's a friend honking their horn. V without a subscript is the speed of sound. So that's top and bottom. The V without the subscript is the speed of sound. So 343 meters per second, unless we're told otherwise. V sub O is the speed of the observer. V sub S is the speed of the source. Now granted, if one of them is stationary, you're just simply going to put in 0 for the stationary one. If they're both stationary, then this ratio becomes 1, and you hear the actual frequency. Okay. Now the signs. There's a reason I put it as plus over minus on top and minus over plus on bottom. On the top, the positive sign is used if the observer moves towards the source. The negative sign is if the observer is moving away. In the denominator, the minus sign is if the source is moving towards the observer. The positive sign is the source moves away from the observer. So they're put in the order they are so that the top sign always relates to motion towards and the bottom sign always relates to motion away. So for example, let's say we're driving down the freeway. I don't have very good artistic skills, I apologize. So we have a cop car coming down, barreling up behind us on the freeway. So we're traveling 35 meters per second. The cop car is traveling 45 meters per second. We're going to pretend we're in the same lane so that the motion is directly in a straight line. This equation, VO and VS, are specifically the components of the velocity that are directly towards or away from us. That's why the pitch continually changes. So if you're on the side of the road listening to a car go by, the pitch changes. It keeps getting higher and higher and higher and then lower and lower and lower. And that's because the component of the velocity directly towards you or directly away from you keeps changing. So we're going to pretend we're in the same lane so the cop car is driving directly towards us. But he's not going to hit us. I don't actually know what frequency a cop siren emits, but let's just make one up. Let's say it's 450 hertz. What frequency will we hear because of this motion? Will you expect to hear something higher or lower than the 450? Higher. Why? Relative motion is that the cop car is gaining on us. It's moving towards us. Now, unfortunately, this equation doesn't work where we could just take the difference between the velocity and use it that way and say that we're stationary and the cop was moving at 10 meters per second. The equation doesn't work that way. You have to use the actual values for each. So the frequency we hear is going to be related to the 450 hertz that is actually being emitted. The speed of sound is 343 meters per second. The observer is us, so the observer is traveling 35 meters per second. The source is traveling 45 meters per second. Now it's the signs that we have to consider. In the numerator, the sign is chosen depending upon what the observer specifically is doing. Us, are we driving towards the cop car or away from the cop car? Away. So we need to use the negative sign in the numerator. It doesn't matter that the cop car is gaining on us. In the denominator, it's what the source is doing. So is the cop car driving towards us or away? Towards as well. So we need a negative sign in the denominator as well. So plugging and chugging at this point. 343, minus 35. Please let me know if you get anything different, if you're plugging along. So we do get higher, as we expected. So 465 hertz would be the frequency we would actually hear.
How much of a shift is that? In the sound? Or is
it's actually not very much in terms of like the piano keyboard in terms of notes.
Like how much would a half step be?
In order to go an octave, you have to double the frequency. So I'm not exactly sure how much the half step would be. So it wouldn't be huge, no. Okay. How could we get an even higher frequency?
Turn around.
Turn around. Us head that way. So heading towards a head-on collision. Just don't collide. So if you're both headed towards each other, this would have ended up being positive because we would be driving towards the cop car. This would still be negative, so we get an even bigger ratio.
What would the sign be if one of the observer or the source is stationary? Would that be considered?
If one of them is stationary, does it really matter if you add 0 or subtract 0? It's okay. That's always a question.
If the cop car was going slower than the 35 miles per hour, but still traveling towards, because it's the other car is going faster, would it still be going away or towards?
You'd still consider being towards, but with this number being smaller, the net result would have been smaller than 450. You'd get a ratio that was smaller. It's a good question. So if the cop car was still traveling, if we were traveling in the same directions, but if the cop car was going slower than 35, our signs would be correct here. We just have a different number here, which would change the ratio overall. Okay. Now with light, let me hurry and give you the equations for light. They're very similar. We don't worry about the observer's motion in terms of light. If we're analyzing light from distant stars, we just consider ourselves stationary. So we don't worry about towards or away as far as the observer is. So for light, the redshift. Now, your book gives us the equations in terms of wavelength, which can easily be converted to frequency if you want frequency. So lambda naught's the actual wavelength of the light being emitted. Vs is the speed of the source, so the speed of the star. C is the speed of light in a vacuum. Redshift is specifically, you're perceiving a longer wavelength, therefore it's moving away from you. Blue shift is towards. The equation looks almost identical. The signs just change. So it's positive in the numerator and negative in the denominator for the redshift, and opposite for the blue shift.
So on the VS, that's just velocity of the source?
The source, yeah. So Vs is the speed of the source, however fast it's traveling. And this only tells us specifically how fast it's traveling directly towards or away from us. It doesn't tell us anything about motion perpendicular to that. Okay. So, for example, astronomers right now have observed on a whole an overall universal redshift. So in general, universally, things are moving away from each other. Now, if you look object by object, they're not all moving away from us. But as an average, on average, things are moving away. So they believe, at this point, that the universe is expanding. And not only are they moving away, but things that are farther away from us are moving faster than things that are closer. So they believe the universe is accelerating in its expansion. So it's a useful tool for astronomers.
One question about, you said if the car's not going straight at you, you won't hear the Doppler effect. Is it just because it's not
No,
as
you will
dramatic?
hear the Doppler effect. Well, as long as there's any component of motion towards you. But for example, if you were actually standing on the side of the road with a car driving down, you wouldn't hear a constant pitch. The pitch would actually keep getting bigger and bigger and bigger as it approached you, and then lower and lower and lower as it receded away. Because the component of the velocity that points towards you is changing. So, technically, to actually hear a constant pitch, you would have to be standing in the way of the car. So, you need to be Superman or something so you could jump out of the way and let it go past. So, yes.